complex numbers. If we ever want to find a root for a polynomial, and roots are basically my zeros or my x-intercepts mostly. So when I want to find a root, I'm really saying, let's let the equation equal 0. So for example, here I have x squared plus 1 equals 0. If I subtracted 1 from both sides, I would end up with x squared equals -1. And there's no square root of -1 in the real numbers, because the square root of 1 is 1, because 1 times 1 is 1. But even if it was -1 times -1, it's still +1. You can see that there's no actual square root of -1. So what we say is that this is equal to I. And they call that the imaginary part of my complex number. All complex numbers are always of the form a plus bi, where a is the real part, a is the real part, and bi is the imaginary part. For example, let's say I have I equals the square root of -1. Well, what happens when I square both sides? So when I square both sides, I get I squared equals, and notice the square root and the square are always going to cancel, right? So I get I squared equals -1. That's my second one. If I multiply both sides by I'll have I cubed equals -I. And again, if I multiply both sides by I again, I would have I to the 4th. Here I would say, instead of saying 1, let's say it's -I squared. But we know from before that I squared equals -1. So it's really the same as -1, which is the same as +1. And basically, that's what happens. If I were to look at this in a different way, let's say this is I multiply by I get I squared equals -1. I multiply by I again, I get I cubed. I'm going this way. I get I cubed is equal to -I. I multiply by I again, I get I to the 4th is equal to 1. And notice if I multiply by I again, I'll go back to I because I'm already at 1, right? So I to the 5th is the same as I. Let's say I have I to the 75th power. Remember I said all complex numbers have to be of the form a plus bi? Notice it doesn't say anything about a plus bi to some power. So I have to be able to turn that I to the 75th power into some power where it's either I to the 0 or I to the 1 power. Here's what I'm going to do. Because I know that I to the 4th is always equal to 1, what I'm going to do is I'm going to divide this by 4, which gives me 1, that gives me 4, 35 is 8, so that would be 32. So I'd have a remainder of 3. So here, if I divide 75 by 4, I get 18 with a remainder of 3. Now, that means if I put it into exponent notation, this is the same as I to the 4th power to the 18th power, because I'm going to multiply those exponents, which gives me 72. And then I'm going to I need 3 more to make it 75. Well, we said that I to the 4th is 1. And 1 to any power is going to be 1. So this is really going to just disappear, because it's going to be 1 times whatever's left. And that whatever's left is I to the 3rd, which is equal to -I. Now I can say I to the 75th power is equal to -I. Now, I don't expect you to go through the whole process and show all your work. All you really need to remember is that the remainder is always going to be how many i's I have left over. Let's say I'd say your I to the 200th power. I divide that by 4, I get I to the 4th power to the 50th power, but there's no remainder. So that would just be I to the 0 power, which is the same as 1. With complex numbers or imaginary numbers, you just add the real part together, and then you add the imaginary part together, just like you would add a variable, or you multiply. I plus I is 2I, 3I minus 4I is minus I, 5 times 3I is 15I, just like you would expect. Nothing out of the ordinary. So here, if I have I times I get I squared. And I said I squared is -1. I'm not going to go through these. Well, I can just say this is -I, this is 1. This would be the same as 14I squared. But remember, it has to be of the form A plus BI. So I don't have an I squared. I squared is equal to -1. So this is really the same as -14. So if I wanted to say it's in the form of A plus BI, which is all complex numbers, I would say this is -14 plus 0I, which still makes it a complex number. I already talked about this. So we have A plus BI. A is the real part, B is the imaginary part. There's really nothing much here. A is the real part. And if I only have a real number, then B could equal 0. If I only have the imaginary part, then A would equal 0. So here, for example, I could say 2. That still can be a complex number because I'm just not putting in this part. So when we have two complex numbers and we say they're equal, we have to say that A has to equal C because that's the real part, and B has to equal D. That's all this slide basically says. Again, addition and subtraction is pretty simple. I'm not going to do the first one because I'm pretty sure everybody can do the first one. It's pretty simple. You just distribute that negative. I'm going to do the second one because it's got some radicals in there that are going to do something. So I'm going to use all my side here to do it. So the first thing I'm going to do is I'm going to just take off my parentheses. So I have 8 plus the square root of -18. And then I'm going to distribute my negative. So I have -4 minus 3i times the square root of 2. So I have my real part. And I'm not really sure what's happening with the imaginary part. So do you know how to simplify the square root of -18?
You take out, you can take out like a 6 and a 3.
Well, let's do it over here. So we have 18. The easiest way to do this, there's a couple ways, but the easiest way to do this is just a factor, using a factor tree. 18 is 2 times 9, and 9 is 3 times 3, right?
Yeah.
So I can say this, and I have a negative. So basically what I can say is this is really the same as the square root of -1 times the square root of 18, right? Okay. And the square root of -1 is I. So I'm going to go in a lot of different steps. So the square root of 18 is the same as the square root of 2 times 3 times 3, which is really the same thing as the square root of 2 times the square root of 3 squared. So I can say this is really equal to 3 times the square root of 2. Does that make sense?
Yeah, but what happened to the square root?
Well, what's the square root of 3 squared?
2.
No, the square root of 3 squared. So the square root of 3 squared is really equal to the square root of 9, right? Which is 3. So, so this becomes 3, and that's my square root of 2 right there.
Gotcha. Yep.
Okay, good. So now I have 8 plus, and I have 3 times the square root of 2i minus 4 plus 3 plus 3i times the square root of 2. And I can see that I can cancel this 3 times the square root of 2i with minus 3 times the square root of 2i. And my final answer is 4. Which is not that obvious when you look at this, because you do have to simplify those radicals to see if they match. When I want to do multiplication on complex numbers, I really just do FOIL.
Yeah.
Just look at it like two binomials. FOIL would be first times first, outer times outer, inner times inner, and last times last, right? And then I'm going to combine like terms. I have 12. I can combine these two to be minus 22i plus 6i squared. I squared. What does I squared equal?
-1.
-1. So this becomes 12 minus 22i plus 6 times -1, which is -6. 12 minus 6 is 6. So my final answer here would be 6 minus 22i.
Okay, and that's in the form, right?
And that's in the form a plus bi, because a would be 6, b would be 22. And we have the now the hardest part is going to be the division. We have something called conjugates. It's a word some of you probably have heard before, maybe you don't know what it means. But basically, if you look at the difference of squares, let's say a squared minus b squared, that's always can be factored to a plus b times a minus b, right? These are conjugates. They're not complex conjugates because I haven't said there's an I anywhere, but they are conjugates. Complex conjugates are basically a plus bi times a minus bi. And because of the way that works, if we multiply them out, like we FOIL it, which is what this is done, I can see that the middle term is going to cancel. And I'm going to end up with a squared minus b squared times I squared. And I squared is -1. So I end up with a squared plus b squared. So remember when we said in the past that we couldn't factor a squared plus b squared? Well, now we can factor it. A squared plus b squared can be factored into a plus bi times a minus bi. So as long as you have that I, you actually get that plus sign between them. And why is this important? Well, when we want to do division, if we start, this looks more complicated than it needs to. I'll do a problem. So if we start with something like this, I can see this is division of two complex numbers, and it is definitely not of the form a plus bi. It's not my answer. Have to turn it into something where it's a plus bi. Now, the best thing to do when I want to do that is I want to take the conjugate, and I want to take the conjugate of the denominator. Because if I can make the denominator into a number, I can separate it into two fractions. My conjugate for 1 minus 2i, what would be the conjugate for 1 minus 2i? All you're doing is changing the sign. So if you have a plus b, the conjugate is a minus b.
Oh.
That's it.
Okay.
If you have a plus bi,
The
conjugate a minus bi. Exactly.
Okay. So
Okay.
it's just 1 plus 2i.
Perfect. So I'm going to multiply the denominator by 1 plus 2i. If I do that, I also have to multiply the numerator by that. That way I haven't changed the number. All I've done is multiply by 1, right? It's going to look different, but I'm still just multiplying by 1. In the numerator, I'm just going to FOIL. So I get first times first, outer times outer, inner times inner, and last times last, right?
Yep.
And I can do the same thing in the denominator, but honestly, the best thing, I mean, starting now, if you have a plus b times a minus b, it's always a square. It's the difference of squares. Okay. So if you have a plus bi times a minus bi, it's always going to be a squared plus b squared. The middle terms are still going to cancel.
Okay.
Okay, so here, instead of foiling the whole thing out, I can just say this is going to be a is 1, so it's going to be 1 squared, plus b is 2, so it's going to be 4, right? Does that make sense? Do you want me to do it out so you can see how it works?
Okay. I see what you're talking about with 1 plus 2i. Okay. Yeah.
Because really we're really still doing the same thing. 1 squared is 1, 2i squared is 4i squared, but because it's I squared, it becomes negative. So that's what changes it to a positive. Okay.
Okay, yeah. That I get. Yep.
Perfect. So here I have 6 plus 5i, and I have minus 14i squared. I squared is negative 1, so that turns the 14 positive. And then I have divided by 5, which is going to equal 20 plus 5i divided by 5. And now I can say this is really the same as 20 over 5 plus 5i over 5, which is equal to 4 plus I. And now notice it's in standard form. I've divided two complex numbers. I've come out with something that is a complex number in the correct form. I want to write this in standard form, which is a plus bi. Anytime you see standard form for complex numbers, a plus bi. The easiest thing to do is find a common denominator. Or we can turn these both into standard form and then just add the numbers together. If I turn 1 plus I over I into standard form a plus bi, then it's going to be easy to add it to another a plus bi. We're going to look at first 1 plus I over I. And I really need to get rid of the I in the denominator because I can't have any I's in the denominator. They can only be in the numerator. I can multiply both the top and the bottom by I, right?
Mm-hmm.
Because that would give me, I'll just multiply it out. I have I plus I squared over I squared, which is the same thing as I minus 1 over minus 1. If I multiply the numerator and the denominator by a negative number, this really becomes 1 minus I over 1, or 1 minus I. I don't know if you got that. So I'm multiplying by negative 1 over negative 1. That way I have a positive I in the denominator. Now I'm going to do the same thing here. I have 3 over 4 minus I. So what do you think I can multiply that by?
Could you just multiply by 4 minus I? Or
not 4 minus I, the conjugate, which is
4 plus I.
There you go. So if I multiply this by 4 plus I over 4 plus I, then in the numerator I get 12 plus 3i over, and what would happen? Don't foil it. Just tell me if you have any idea what 4 minus I times 4 plus I would be. Remember, a plus b times a minus b equals a squared minus b squared.
Oh, the
A is going to be 4, right?
Yeah.
So 4 squared is 16.
Yeah.
And b is going to be I, right?
Mm-hmm.
So that's going to be minus I squared.
When you mean
square each term, and then you put like you don't have to put the minus. I'm just kind of doing it out in more steps. So this is 12 plus 3i over, well, I squared is negative 1, right? So 16 minus 1 is 16 plus 1, or 17. What I want to do is I want to put this in standard form. Standard form is a plus bi. So the real part is 12/17, and the imaginary part is 3/17. I have 1 minus I minus 12/17 plus 3/17 I. And now we just add the real parts. 1 minus 12/17 is 5/17. And then I have minus I. If I distribute that negative, that's me minus 3/17 I. So that's minus 1 minus 3/17. Minus 1 is 17/17. So 17/17 minus 3/17 is minus 20/17 I. And now notice it is in standard form.